So hopefully my screen doesn't freeze up this time. So today we're going to go through learning about exponents and radicals, which I'm just going to go through some of the more basic parts of it. So yeah, okay. So I'll start going through the lesson that I have today. Okay. So for exponents, so I have some definitions. I'm going to underline them in a nicer color so maybe you can see it better. I'll use maybe, okay. So positive exponent. So you probably have seen an exponent before. So we have, let's say we have 2. How about 2? Okay, 2 squared, right? So this little number here is what we call the exponent. Okay, and this bottom number, the big one, is what we call the base. And so the base is raised to the power of an exponent. So here I would say out loud, I would say 2 to the second power or 2 squared or something. And this just means that it's 2 multiplied by itself 2 times. So 2 times 2, and that's 4, right? And so that's the basic gist of how an exponent works. So let me move this over. And let's do a different one maybe. So how about 3 cubed? So the base is 3, right? So the base is 3 and our exponent is also 3. So that's the exponent. And this just means that we have 3 multiplied to itself 3 times. So 3 times 3 times 3. And so 3 times 3 is 9, right? And 9 times another 3 is 27. So 3 cubed, or 3 to the third power, is going to equal 27. So that's kind of the basic gist of how exponents work. You've probably seen them before. So what if I had what if I had 5 to the first power? 5 is the base and 1 is the exponent. That just means that 5 is multiplied to itself 1 time, right? So 5 is just there. It's not multiplied to anything. I should have worded that better, but it's just 5, right? So it's just 5 once. If it was 5 squared, it would be 5 times 5, right? But that's not what the problem had. So 5 to the first power is 5. So anything to the first power is going to be itself. So maybe I had 10 to the first power, it's going to be 10. Or even if I had like -2 to the first power, that is going to equal -2. It's going to stay the same. So anything to the first power is just itself. And then, okay, so at this point here, bases can also be variables. So here I have x squared. So x squared, I'm like writing all over the place. So x squared, this just means I have x multiplied to itself. So that's just x times x. What if I had x to the fifth? So x to the fifth would be x times x times x times x times x, right? You got the idea. So it's x multiplied 5 times. And so you can do this with any variable. So p cubed would be p times p times p, so on and so forth. Okay. So here we have 0 exponent. Any number raised to 0 power is 1 except for 0. So what if I had, I don't know, I want to switch a color. Here we go. What if we had 25 to the 0th power? 25 to the 0th power is going to be 1 because anything to the 0th power is going to be 1. What if I had x, y, z in parentheses to the 0th power? That would just be 1. Again, it doesn't matter what it is, just so as long as x y, and z aren't 0, that's going to be 1. So the only exception to this rule is where we have 0 to the power of 0, because that's, by definition, it's going to be undefined. So 0 to the power of 0 is undefined. But anything else raised to the 0th power is going to be 1. Okay. So those first few points were pretty simple, right? So this is probably going to be the most difficult one, which is the negative exponent, which I think a lot of people will have trouble with at first. So a negative exponent is a number raised to a negative number, right? So instead of the exponent being a positive number, we now have a negative number. So when we raise a number to a negative exponent, we're basically going to take the reciprocal of that number raised to the positive exponent. I'm going to show you an example, because sometimes when it's better to show an example rather than to say. I'm going to move this off to the side. Yeah. I'm afraid that it'll get messy here, so I'm going to do this. Okay. So what if we have a negative exponent? So let's just do some examples, and I'll kind of show you what I'm talking about. So what if I had 4 to the negative 2? Well, I know that 4 to the power of 2 is going to be 16, right? Because 4 times 4, that means 4 is multiplied to itself once. 4 times 4 is going to be 16. So 4 squared is 16. What about 4 to the negative 2? 4 to the negative 2 is going to actually be 1 over 16. So what did I just do? So that basically means anytime I have a negative exponent, I'm basically putting this into the denominator, but changing the negative exponent to a positive exponent. So 1 over 4 squared, well, we just said 4 squared is 16. So this final answer is going to be 1 over 16. So whenever I have a negative exponent, I just put the regular exponent in the denominator. So let's do another example. 15 to the negative 1. So 15 to the negative 1. So this is going to turn into, whenever we see a negative, I have to think, oh, I have to put this in the denominator now. And just take away the negative. This is going to turn into 1 over 15 to the first power, right? We just said that 15 or anything to the first power is itself. So that's basically just going to be 1 over 15. And I'll do another for good measure. Actually, there's going to be another example of this. So let me move this down here. So that's basically how a negative exponent works. So it's kind of the most complicated part here, but at least the examples we'll be working with here are not that bad. Okay, so let's go through some problems. So our first one, here we have 2 to the negative third power. And so a similar procedure, right? So 2 to the negative third power equals what? Whenever we see a negative exponent, we have to think, oh, this thing belongs in the denominator. And then we just take away that negative. So 1 over 2 to the positive third power now. So that is also going to be 1 over 2 times 2 times 2, right? Because 2 cubed, 2 to the third power means that I'm multiplying 2 together 3 times. So 1 over 2 times 2 times 2. 2 times 2 times 2 is going to be, these two multiply is going to be 4, right? 4 times 2 is going to be 8. So this whole thing is going to be 8. Make this prettier. So your final answer is going to be 1/8. Right, so not that bad. So now these next few are going to be a bit more difficult, or these next couple, because they involve negative numbers. And this is something that will trip up a lot of people, dealing with negative numbers and exponents. And it causes a lot of dumb mistakes as well. So we'll go through a bit slowly. So here, oops, gosh. There we go. So here, in this example, we have -3 to the -4th power. So there's two negatives that we have to take care of here, right? Let me rewrite it. -3 to the -4th power. We have two negatives that are kind of places where we could make a mistake. So we have to be really careful. There's this negative and this negative, right? So it's up to you which one you want to deal with first. I'm gonna take care of this one first. I'm gonna get rid of that negative. So when we have a negative in the exponent, remember, we just stick the whole thing in the denominator, but change the exponent to a positive number. So now I have -3 to the 4th power. I still need these parentheses though. Don't drop them. If they're in the original problem, don't take away the parentheses. And you'll kind of see why in a bit. So if I have 1 over -3 to the 4th power, this actually means I'm going to have -3 multiplied to itself 4 times. So it's going to be -3 times -3 times -3 times -3. Hopefully this is big enough so you can see it. Now I'm going to move this over because I need more space. Okay. So -3 times -3 times -3 times -3. That's a lot, right? But we can kind of simplify it easily by saying, well, -3 times -3 is +9, right? Because a negative number times a negative number is going to be a positive number. So that's 9. This is also going to be 9, right? It's just the same thing. So now we have 9 times 9. 9 times 9 is going to be +81, right? And so that's it. So 1 over 81 is going to be that answer. So notice how we had two negatives at the beginning of the problem, but I got rid of this negative first by sticking the whole thing in the denominator, right? Oops. And then I took care of the negative inside the parentheses. So right here, we have to make sure that each 3 is carrying a negative. So that's really important that each 3 has a negative. And that's what these parentheses mean. When you have those parentheses, that means it's -3 multiplied to each other 4 times. And so this next problem is a bit different, right? So again, it's -3 to the -4th power, but what's different? We don't have those parentheses, right? We don't have the parentheses, so we just have this. Let's try doing the same thing. So let's try getting rid of this negative first, okay? So that negative in there, if a negative is in the exponent, remember we have to shift the whole thing into the denominator of the fraction, right? So 1 over, and then we have -3 to the 4th now. So this got changed to a positive, right? See what I just did? So the -4 got changed into a +4. So what about the -3? Well, there's no parentheses in here, right? So if you're unfamiliar with this, you might say, oh, well, that's going to be -1 or 1 over -3 times -3 times -3 times -3, right? But then this is going to be the exact same as that problem. And that's actually not the case. If we do not have the parentheses around the -3, like if we didn't have these, then that means it's negative in the front. We have a negative in the front, but that's only multiplied once. And then the inside is going to be -3 times 3 times 3 times 3, or -3 to the 4th. So I'm going to explain that again. So it's not going to be this. It's not going to be -3 times -3 times -3 times -3. It's not that. There's just going to be one negative multiplied at the beginning, and then 3 times 3 times 3 times 3. See the difference? So here I had like 4 negatives, right? We have one here, one here, one here, and one here. But here, we just have the 1 negative, and that's this. This negative directly goes here. And inside the parentheses are all positive 3s. And so that's like a really important difference between this problem and this problem, is those parentheses are very important. And it's really easy to make a mistake there. So make sure if you have the parentheses, it's going to be -3 times -3 times -3 times -3. But when you don't have parentheses, if you just have the negative hanging out over here, that just means, oh, we have 1 negative sign. And then these 3s are going to be positive, basically. So that's a really important distinguishing part to make. So it's really important to remember that. Anyways, let's solve the rest of the problem. So -3 times positive 3 times 3 times 3 times 3. So this is going to be 9, right? 3 times 3 is 9. Another 3 times 3 is 9. Oops, 9. So 9 times 9 is going to be 81. But we have this negative here, so don't remember in our final answer, we need to have that negative. So 1 over -81, or you could put the negative on the top here, but it doesn't really matter. It's the same exact thing. Who cares, as long as we have it right, right? So the difference, this had parentheses, and this answer ended up being positive. This didn't have parentheses, and this answer ended up being negative. So I think that's probably one of the most important parts. So anyways, hopefully that makes sense. So let's move on to these next couple of problems. Okay. So here's the next example. Not that bad. 3 times y to the negative second power. So we have 3 times y to the negative second power. So I want to get rid of that negative, right? Anytime I see a negative in the exponent, my first instinct is I don't want it there. Because it's really easy to forget and make a mistake, or maybe you'll read it accidentally as 3y squared and you'll solve it like this, which, I mean, there's nothing to simplify here, but you might accidentally read it as 3y to the positive 2, but it's actually to the negative 2. So here, the main thing is that I want to get rid of the negative sign. So ignoring the 3 for a little bit, we're going to kind of ignore the 3 because the 3 is just multiplied, right? Nothing changes there. So let's just look at this part. Y to negative. So remember, when we have a negative in the exponent, I'm going to put this whole thing in the denominator, but without the negative. So 1 over y squared. So that's how we get rid of the negative. Hopefully that's clear. And then the rest of it is just, well, we have this 3 here. We can't forget it, right? Now we just need to multiply the 3 to this. So it's going to be 3 times 1 over y squared, which is going to end up being 3 over y squared. That looks prettier, right? So that's it. Pretty simple. That was just getting rid of the negative in the exponent. What about this next one? So this next one's kind of similar. So I'm going to rewrite it because Microsoft hates me. So -4 divided by k to the -4. So it looks a bit more complicated, right? Because there's 2 negatives. Well, one of them we don't really need to care about, which is this one, right? -4 is going to stay a -4. It's not raised to any power. So I don't really need to worry about it. It just stays there. What I do need to worry about is this negative. Is that negative? Any negative in an exponent, I don't want it there. I want to get rid of it. So the difference, though, in this problem is that the negative exponent is in the denominator, right? It's in the denominator of the fraction, whereas in all of these other problems, our negative exponent was not in a fraction. It was in the numerator, basically. So that's where it gets a bit different. So let's just look at this part alone. Let's just look at 1 over k to -4. And let's just leave the -4 alone for now. So let's just pretend that we don't have that. So 1 over k to the -4. Well, we just established that if we have a negative in the exponent, I'm going to pretend that this is in a fraction in the denominator, but raise the positive exponent, right? So raise the positive 4. So this numerator stays the same. It's just 1. But see the difference? So when I have k to the negative 4 here, I put it in a fraction when the denominator is here. So it's 1 divided by 1 over k to the 4th. And so this is where you should kind of know how to divide fractions, because now it's pretty simple, right? So if it's 1, if you're dividing by fraction, right, you're basically just multiplying by the reciprocal. So this flipped over. So when I flip 1 over k to the 4th, now I have k to the 4th over 1. So hopefully you see what I did there. When I divide a fraction, that denominator is always going to turn into the reciprocal. So I have 1. This and this are the same thing, right? And then this and this are reciprocals of each other. So now k to the 4th goes at the top, and the 1 goes to the bottom. So hopefully that makes sense. And from here it's easy. So here I have 1 over 1 times k to the 4th over 1. All these 1s are the same, right? So 1 multiplied by anything is 1. So that's going to equal k to the 4th, basically. So we're not done yet, right? Because we still have this thing. We still have to add the negative 4 to it. Or not add, but technically multiply. So we can't forget about the negative 4. So bringing that negative 4 all the way here, I have negative 4 times k to the 4th. So it looks pretty similar to the original thing, actually. But it's just that we have k to the positive 4 in the numerator now. So that's the difference. And so hopefully that makes sense. And yes, I can read it. Okay, good. My handwriting is legible. So hopefully that makes sense. So negative exponents are kind of what I wanted to get at there, because they're probably the most difficult thing to wrap your head around. Okay, so here, this is some kind of application stuff. So we have scientific notation and powers of 10. So powers of 10, by that I mean like 10 to the 7th maybe, or any 10 raised to any exponent. 10 to the 4th, 10 to the 6th, dot, dot, dot. It could be any number in this exponent, right? Any number in that exponent is a power of 10. So powers of 10 can be used to write extremely big or extremely small numbers easily, because no one wants to write out 10 zeros for a number, right? So like in real life word problems, maybe we're going to say, oh, there's this satellite that's orbiting some hundreds of thousands of miles away from the Earth. But when I'm writing that distance, I don't want to do this, right? Because writing out all those zeros takes so much time. And so this is kind of a way to condense that, right? So I don't need to write as many zeros, because writing a lot of zeros is not going to help any of us. So here we're going to try to learn how to condense that. So let's see. So let's move on. Each time you multiply a number by 10, the exponent increases by 1, and a decimal point moves 1 place to the right. So let's say I have 10 multiplied by 10. So originally, let's say I had just 10 to the 1st power. So that's 10, right? And then let's say I decide to multiply that by 10. We all know that 10 times 10 is 100, right? 10 times 10 is 100. And 100 is also 10 squared, right? 10 squared is 10 times 10. So here the point is, this exponent is going to increase by 1 every single time I multiply it by 10. And that decimal point moves 1 place to the right. So first I had 10. The decimal point is here. Now I have 100. So this decimal point essentially moved 1 place to the right, and now I have an extra 0 here. So now the decimal point is here. That's basically what it means. Let's see. So the next thing, each time, forgot to capitalize, each time you divide a number by 10, the exponent decreases by 1, and the decimal point moves 1 place to the left. So let's use 10 to the first again. So 10 to the first power is 10, right? Oh, Jesus. My screen skipped again. Anyways, so here, I'll explain this one, hopefully, and makes more sense now that it's not skipping anymore. So 10 to the first power is 10, right? Now, what if I tried to divide that number by 10? So 10 divided by 10. So 10 divided by 10 is going to be 1, right? And 1 is also 10 to the 0th power, right? Anything to the 0th power is going to be 1. So here, my exponent decreased by 1. It went from going from 1 to 0. And so that's what's going to happen anytime you divide a number by 10. Okay. And the decimal point moves 1 place to the left. Well, oops, I should use black. So I had 10 originally. And now I divide by 10, I get 1, right? So this decimal point used to be here. Now it moved 1 place to the left, right? So now my decimal point is here, right, directly to the right of 1. So this is multiplying. When I multiply by 10, this number increases by 1. When I divide by 10, this number decreases by 1. So when I divide by 10, by 10. Okay. Okay, so we have some practice to familiarize ourselves with this. So first example, write each number as a power of 10. So here, let's do these 3. So there are 3 different examples. So this one is 10 million, right? So it's 10 million. So let's write out 10 million. 10. See how much time it takes to write all those zeros. So how much time it took to write out all these zeros, we can easily reduce by writing it as 10 to the power of, 10 to the power of a certain number, which I put a question mark. So basically this problem is asking us, what's this number? Well, the way I do it is I start from here, 1, and I count the number of times I had to move my decimal point to the right. And when I get here, the number of little bumps I made is going to tell me how many times I multiplied by 10. So let's count. So first my decimal point was here, right? So how many times I'm multiplying by 10? Here once. So that's 1 time, 2 times, 3 times, 4 times, 5 times, 6 times, 7 times. So that's kind of small. But basically I multiplied 10 7 times in order to make 10 million. So that question mark is going to be 7. So multiplying by 10 because my number gets much, much bigger than 1. So I'm kind of acting like I'm starting from 1. How many times did I multiply by 10 in order to get this big number? All right, what about this? So 0.001. So 0.001. So here I'm also going to start at 1. But pretend my decimal point is here. Now my decimal point moved to the left, right? So we're going to count by 10 in order to move to the right, right? Oh my gosh, what happened? My computer. Okay, there we go. So how many times do I have to divide by 10 to get here? Well, starting from this point, I divided by 10 1 time, divided by 10 2 times, divided by 10 3 times, right? In order to get to this decimal point. So if I divide it by 3, That's actually going to give me 10 to the negative 3. So 10 to the negative 3, if we want to check ourselves and use the exponent rule, right, the negative exponent rule, this would be 1 over 10 to the positive 3, right? Which is 1 over 1,000. And if I want to check this in the calculator and I put in 1 divided by 1,000, you're going to get 0.001. So that's how you know that you're right. So in this first problem, I multiplied by 10s, so I moved to the right, right? But in the second problem, I divided by 10s, so I moved to the left. And then this last one should not be that bad, 10. So 10, I start at 1, and I had to move how many times to the right? I only need to move once to the right, right? In order to get to 10. That means the question mark is going to be 1. So 10 to the first power. So I'm going to box my answers. So this one's 10 to the 7th, 10 to the negative 3, 10 to the first power. So notice how all the answers have 10 as the base, and then a different number as an exponent each time. So that's the point here. You will start with 10, raise it to some power. Okay. So here, write out the value of this expression. It's basically asking me to write out all the zeros. So I have 19.5 times 10 to the negative 4. So I could do this. I could say, well, 10 to the negative 4, I'm going to convert it. So it's 1 over 10 to the 4th, right? Times 19.5. This thing stays the same. And then I could do that math, right? I could punch that in the calculator and get my answer. Well, I'm going to do something different. So 19.5 times 10 to the negative 4. So what does the negative 4 mean? Negative 4 means, like, what if I start my decimal point here? My decimal point starts here, right? Right here. If I'm multiplying by 10 to the negative 4, that means I'm going to divide by 10 4 times. So basically, I'm going to take my dot and go here. 1, 2, 3, 4. So my number is getting much, much smaller. And so here I just write placeholder zeros, something like this. So let me write that in a nicer way, though. So here, 19.5. So when I multiply by 10 to the negative 4, I'm doing this. Well, I know that I'm going to be moving my decimal to the left 4 times. So 1 time, 2 times, so right here, right before the 1, 3 times. So I'm going to add a 0, 4 times, another 0 here. So now my new decimal point is all the way over here. So notice my new number is much smaller than 19.5. So let me write that cleaner. 0.00195. So the decimal point used to be here, now it jumped all the way over here. And notice how that's 4 places. Okay. So now I'm going to introduce scientific notation. So scientific notation is a better way of writing out really big numbers. So there are 2 parts to this. There are 2 parts. So the first part is going to be a number between 1 and 10. So let's say I pick 5. I don't know. Or it could be 9.999. Who cares? It could be any number between 1 and 10. So maybe I choose 1.2. And the second part is the power of 10. So we multiply by the second part. So 10, I could pick any number in the exponent. So maybe 3. And so this is proper scientific notation. So this is the first part. And this is the second part. So basically, we want to be able to flip between scientific notation, which is this thing, and normal numbers, which is writing out all the zeros. So here we have a nice problem to show us how to do that. So Jupiter has a diameter of about 143,000 kilometers. Its shortest distance from the Earth is about 5.91 times 10 to the 8th kilometers. Its average distance from the Sun is about 778,400,000 kilometers. So those are a lot of really big numbers, right? So write Jupiter's shortest distance from Earth in standard form. So in standard form. So standard form means the actual number itself. So the actual number. So Jupiter's shortest distance from the Earth. In the problem, I think it was, let me choose a color, green. I think it was this. 5.91 times 10 to the 8th was the shortest distance from Earth, right? So I'm basically going to turn this into a huge number form. And so that basically means what? I'm multiplying by 10 8 times. So I'm basically moving this decimal point to the right 8 times. So it's going to be a lot of arrows drawing. So 5, 9, 1. So the decimal was originally over here. I'm moving to the right 8 times. So let's count. 1, 2, 3, 4, 5, 6, 7, 8. So now I put all these placeholder zeros. So the decimal point is going to end up right here, right? Because this is 8 places in total that I have multiplied by 10. So now my final answer, 5, 9, 1. So here it's really hard to count a number of zeros. So we have 1, 2, 3, 4, 5, 6, 0. So that's going to be our answer. I'm going to put commas here just to make it look nicer. And box it. So this is going to be my answer on this one. I should add kilometers. Not too bad. Just counting numbers, counting places. Okay. So what about this next one? So write Jupiter's average distance from the Sun in scientific notation. So in the first problem, we were switching from scientific notation to standard form, right? To our normal number. And now we're doing the opposite. We're converting from a normal number to the scientific notation. So normal number to scientific notation. So Jupiter's average distance from the Sun was this thing, right? So we want to write this in this type of form where we have one number times 10 to the some power. So here, a really easy way to do this is just pick out the first number by saying, well, these are the only numbers that aren't 0. And I know that my first part has to be a number between 1 and 10. So from this, I'm going to put my decimal point starting here. Why? Because that gives me 7.784. This is a number between 1 and 10, right? 7.784 is a number between 1 and 10. And from there, I'm basically going to count the number of times I had to multiply in order to get this many zeros. So let's see. Starting here, 1, 2, 3, and then 4, 5, 6, 7, 8, I think, was how many times we had to multiply in order to get all these zeros. So 1, 2, 3, 4, 5, 6, 7, 8. Yes. So we had to multiply 8 times. So we had to multiply by 10 to the 8th, that means. So this is basically times 10 to the 8th. And so that was a really easy way to do it. So you just choose the number from these numbers that aren't 0. I say, oh, well, I can put my decimal point starting here because that makes a number that is going to be between 1 and 10. Then I count the number of places I had to move to the right in order to get to my original number. Okay. So with the time we have left, we'll do some radical stuff. Okay, it's not too bad. So radicals, so square roots basically are kind of the opposite of squaring something. So we said earlier 2 squared was 4, right? 2 squared means 2 times 2, which is equal to 4. But what if I wanted to undo that? So that would be square root of 4. So the square root of 4 basically means you're trying to find, well, what numbers under here multiply together to make 4, and they have to be the same number. So 2 times 2, right? So the square root of 4 is going to be 2, because I have to multiply 2 by itself once to get 4. So this exponent and this radical are basically opposites of each other. So a radical expression contains a radical sign, which is the square root thing. The expression under the radical sign is called a radicand. This is just vocabulary. So like whatever I put underneath is radicand. It could be x or y or z or any number. And so we're going to try to simplify these. And so it's not that bad. So here, the first example says simplify square root of 2 over 72. I'm going to rewrite it because it's very ugly. Microsoft making it really ugly. So this is what it's supposed to look like. Square root of 2 over 72. So how do we simplify this? Well, first I'm going to notice one thing, and that is that I could simplify this fraction, right? 2 divided by 72. I can simplify that fraction because 72 is divisible by 2, right? 72 divided by 2 is going to be 36. So if I divide both things by 2, I get 1 over 36. And so hopefully you know, I'm not sure if you do, but hopefully you know that 1 over 36, well, 36 is just 6 times 6, right? And the square root of 36 is just going to be one of these 6s. So because 6 squared is 36, so square root of 36 equals 6. I'm basically going from here to here and then backwards. This is basically going backwards. So square root of 1 over 36 is going to be 1 over 6. The square root of 1 is just 1. So this is going to be my answer. Okay, maybe we'll do a couple more because I don't have much time. So let's do this one. So 9 times, I'll rewrite it, 9 times square root of y minus square root of y. So here, I treat square root of y as its own little variable. So basically, I'm going to pretend that there's like kind of a 1 multiplied in front of here, right? So now I can combine like terms. I'm going to write this in green. So 9 minus 1 is going to be 8, right? And if I'm treating square root of y as kind of a variable, it's going to stay the same, right? Nothing happens to the square root y. The only change that happens is the difference between 9 and 1, which is going to be 8 square root y. So I can only do this kind of thing, though, if the thing under the square root is the same. So if I had something like the next problem, so 12 root 2 minus 4 times the square root of 11. If I had something like this, I could not simplify this. This is not possible. So I would just leave my answer like this. And the reason why is because under here we have 2. Under here we have 11. And those two numbers are not the same. So I must have the same thing under the square root. So I could simplify it if it was something like 12 square root 2 minus 4 square root 2. And then I could simplify, combine these like terms. And it would be 12 minus 4 is 8. Square root 2 stays the exact same. So major difference, if the thing under the square root is not the same and you're trying to add or subtract, it will not work. Okay. So I'll do one more for good measure, just this one, which is the easier one. So square root 3 squared plus 4 squared. So what's 3 squared? 3 squared is 3 times 3, right? So 9. And what's 4 squared? 4 squared is 4 times 4, right? Which is going to be 16. What's 9 plus 16? It's going to be 25. And so when I take the square root of 25, well, you might know that 25 is equal to 5 times 5, or 5 squared. And so when we undo that, if we take the square root of 25, that's just going to be this backwards, so it's going to be 5. I can rewrite it, say 5 times 5. And so this is going to leave me with 5. Okay. And so this last one's a bit more complicated. And I'll fill this one out and post it, but anyways, that's mostly the gist of what I wanted to cover today. So exponents, radicals, and scientific notation. Anyways, hope y'all have a good rest of your night, and I will see you tomorrow.